5th International Physics Olympiad, year 1971, IPHO. Problem number 1. A triangular prism of mass big M is placed one side on a frictionless horizontal plane as shown in the figure. The other two sides are inclined with respect to the plane at angles alpha 1 and alpha 2 respectively. Two blocks of masses M1 and M2 connected by an inextensible thread can slide without friction on the surface of the prism. The mass of the pulley which supports the thread is negligible. Express the acceleration A of the blocks relative to the prism in terms of the acceleration A0 of the prism. Find the acceleration A0 of the prism in terms of quantities given and the acceleration g due to gravity. At what ratio m1 over m2 the prism will be in equilibrium. Solution for problem 1. The blocks slide relative to the prism with acceleration a1 and a2, this one and this one, which are parallel to its sides and have the same magnitude a. The blocks move relative to the Earth with acceleration w1 equal a1 plus a0 and w2 equal a2 plus a0. Now we project w1 and w2 along the x and the y axis. For the first body w1 we have in x direction w1x equal a multiplied by cosine alpha 1 minus a0, and in y direction we have w1y equal a sine alpha 1. For body 2 we have in x direction w2x equal a cosine alpha 2 minus alpha 0, and in y direction we have w equal 2y equal a multiplied by sine alpha 2. The equations of motion for the blocks and for the prism have the following vector forms. For the body 1 we have number 7, this one. For number 2 we have this one, and for number 9 we have this one. That's for prism. The forces of tension T1 and T2 at the ends of the thread are of the same magnitude T, since the masses of the thread and that of the pulley are negligible. Note that in equation 1.9 we account for the net force negative T1 plus T2, which the bended thread exerts on the prism through the pulley. The equation of motion results in a system of 6 scalar equations when projected along x and y directions. From number 10 to number 15 we have 6 equations. By adding up equations 10, 12 and 14, all forces internal to the system cancel each other. In this way we obtain the required relation between acceleration a and a0. So for the first question we have a equal a0 multiplied by big M plus M1 plus M2 over M1 cosine alpha 1 plus M2 cosine alpha 2. After that, the straightforward elimination of the unknown forces gives the final answer for a0. And we have a0 equal g multiplied by this coefficient. And finally it follows from equation 17 that the prism will be in equilibrium a0 equals 0 if m1 over m2 equal sine alpha 2 over sine alpha 1. So that was a solution for problem number 1.